This is the second in a series of 5 videos illustrating the MICP user data tool available in CARP. Please view all parts to get a full demonstration of the tool's use and capabilities. In this video we will illustrate the MICP worksheet of the tool. The worksheet has several purposes. First, the Lonoy-predicted MICP curve is compared to a measured MICP curve. Second, the distribution of pore-throat radius for Lonoy-predicted and the measured datasets are compared. Third, the optimized trendline equations for the measured MICP curve are calculated. Fourth, the effective porosities are estimated based on both the predicted and measured datasets. And lastly, the Swanson parameter and the predicted Swanson permeability are calculated. We will start filling in the input data, which are all cells with a yellow background. In this instruction video we will use the pre-filled data. First we enter or paste in measured MICP data, which include capillary pressure and associated saturation. These are columns D and E in the worksheet. The saturation can be entered as mercury saturation or water saturation. The tool will automatically recognize the saturation unit. The general input data in the upper left of the screen refer to well name and sample number, both of which are optional. We also have to enter porosity and the dominant pore type. Optionally, we can also enter our subordinate pore type. We'll leave that empty for now. In the conformance correction input section, we have to answer yes or no to whether we want to carry out conformance correction of the data. If so, we also need to enter the mercury entry pressure. Entry pressure is also needed if we want to calculate the Tomir MICP curve in the deviation worksheet. This will be presented in part 4 of the instruction video. Let's give this a try. Let's answer no to whether we want to perform conformance correction. And the measured MICP curve is the red one, and now we are looking at the raw data. We can click here and we can find out or select the mercury capillary entry pressure. I would select it at 46 psi. So let's perform the conformance correction and enter 46 psi. And before I press the enter, have a close look at this area here on the plot. We see that the conformance correction is being carried out. The effective porosity input section is needed for calculating effective porosity. Effective porosity is porosity constrained by specific pore-throat sizes. The pore-throat radius limit for effective porosity is by default set to 0.3 micrometer, which represents a choke permeability of 1 millidarcy. This number can be changed, and the resulting effective porosities for the predicted and measured MICP curves are given in these 2 green cells. We can, for example, change this to 0.6, and after some calculation we will see that the green cells change to new values. Let's put it back to 0.3. The interfacial tension times the cosinus of the contact angle for mercury air is given in this cell here, and is usually given by the laboratory. The prefilled number is a number applied by many laboratories, but the number can be changed. In the Swanson section, the Swanson parameter and predicted Swanson permeability are given and are based on the MICP curve. Calculation of the Swanson permeability is based on variable pore-type dependent Swanson constants. Now let us go to the predictions made from the input data, which are given by cells with a green background color and as plots. The predicted water saturation and associated pore-throat radiuses for the capillary pressures given in column D are given in columns G and H. The predictions are made based on the Lonoy methodology. The measured and predicted MICP curves are plotted in chart 1. In chart 2, the measured and predicted pore-throat radius distributions are given. In charts 3 and 4, to the far right, we see the power and exponential trend lines for the measured MICP curve, the trendline equations, and their associated R-squared values. The trend lines are derived for capillary pressures between entry pressure and 2000 psi, which is assumed to be close to irreducible water separation.